Hello, I am Attila Egri-Nagy, and my collaborator Miklos Hoffman will appear in the middle of this talk. And we are going to talk about explanations and understanding. So this talk aims to be just a high-level summary of a research project which originated from many years of doing abstract algebra and more recently category theory, and also from our interest in mathematics education. We draw non-mathematical conclusions from mathematical results. Therefore, we are in the realm of philosophy. We start with very general questions. What is understanding and what is an explanation? Of course, we do have some common sense answers, some easy answers, saying like understanding is a process where we go from not knowing to having knowledge, and an explanation just enables this transition. Of course, many branches of science and other fields of knowledge talk about understanding and explanations, but is there a general theory? We are aiming for a general one, a grand theory of understanding. And that's our main observation. So we see that mathematics unintentionally produced a grand theory of understanding. There is a bit of a problem here because depending on your perspective on mathematics, depending on what's your take on the nature of mathematics, you might see this easily or you may not see this observation that easily. So just to help that, we give a simplified story of mathematics, the mathematics how we see it, and we take our embodied existence in this world as the origin of mathematics. So we have an innate number sense. We can instantly recognize small numbers, and we have a geometric intuition. As we evolved in this world with regularities. So that core of mathematics is the same for everyone, as we share the same kind of embodied existence. So we take that core, and then we further develop mathematics with abstraction, which is about forgetting details to make ideas more general, and by creating models, those are analogies and metaphors, so we can extend mathematical ideas creatively. And then, most recently, mathematics got rich enough to be the object of study by itself. So that's exactly what category theory does. It focuses on what is common in different parts of mathematics and how to move between different parts of mathematics. So just to briefly mention two of the main sources for this talk. One is mathematical, and it's written by Saunders Mac-Lane, one of the founders of category theory. And the other one is coming from cognitive science, cognitive linguistics, where they claim that we sort of create mathematics in a metaphorical way. So what's our logic here? Is that if we start with the assumption that mathematics is about understanding the world, and we also see that mathematics studies itself, therefore, mathematics studies the process of understanding. So now it's one of the main tools in mathematics. It's a morphism. That's a structure-preserving map between two different domains. So it's like if we have an object in one domain and we don't know how to deal with that, sometimes we just transform it into another realm, make it represented by another object, which is easier to understand. And there are some common examples. The number line is like that, because you take numbers and you convert them to points on a line. And then, well, you see many of their properties more easily with the geometric intuition. You see as a magnitude, and you can see comparisons. Another example is logarithm, where you can take something more complicated, which is multiplication, and transform it into the realm of addition. And it sort of simplifies the work you need to do. So what's the sort of the basic pattern in this when we want to talk about these domains and the structure preserving maps between? And that's this diagram. So we move from x to y by using the operation a. And this sounds very, very general, and it is. So I can mention a couple of examples how you can imagine these. You can take x and y to be just states, and you have a as the action, the operator, transforming one state into another or taking one state to another. Or you can consider them as a set of statements and the movement is logical inference. Or simply, just in a general way, you can consider them thoughts, and then free or guided association is the movement between them. Or you can go more physical than that and then consider these points as the locations in the city, and the movement between them is walking. And there are many examples, but the key point is that this dynamic relationship, it could replace the fundamental building block of traditional mathematics. That's the state, the set membership, so that one thing belongs to a set. So very important for these movements, this action, is that they are composable. So we can do them one after the other, subject to some conditions, of course. And then now we can say that, well, we can do some work in general by just doing this composition in some domain. If we are working in the domain of logic, then work is that, well, chaining inferences together. So now the idea of the morphism is that, well, we have two different domains to work in. One is the source domain and the other is the target domain. And we do the work, well, it's composition there. And it's like we can switch between them anytime we want if there is a morphic relationship. So it doesn't matter that it's like, oh, we want to do the composition here and then take the result over to the other domain. Or you take the components and then do the composition there. You get the same result. Algebraically, there is this very simple equations, a formula here that expresses this idea. And if you look at it, it's like, oh yeah, this looks like very much like the logarithm equation just before. And yeah, that's right, because that's an example of a morphism. And this may sound still very abstract, so my collaborator will talk about a more concrete example, the example of the cartographic map.
Hello, my name is Miklós Hoffman. I'm from Hungary. I'm a full professor of Esterházy Károly Catholic University. And now I will tell you some words about maps, the most obvious form of appearance of morphism. Maps, for example, in this map of my hometown, Eger, are essential tools to find something somewhere. Tracing lines on the map correspond to walking or driving in town to get to the store, for example. And in everyday practice, it works very well, as the two objects, the city and the drawing, are in a very close correspondence. In the domain of the map, the operation is to follow the road, maybe with your finger, and choose, say, the middle one of the fork, and checking that we have to turn left at the next crossroad. In fact, we connect vertices on the road graph and compose these edges. In reality, we do this with our car driving from one corner to the other, composing the individual segments of roads. What is important here is that this composability of road segments works in real life and in the map in a compatible way. The cartographic map as a planar representation of part of the known world is a very ancient invention. However, in a mathematical sense, it was only at the beginning of the 19th century that Gauss, the famous German mathematician, put map making on a theoretical basis. He discovered that there is no perfect map, and this caused much trouble in real life, for example, for sailors. What do we mean by perfect map? In the ideal case, the map represents the world in an isometric manner, that is, preserving all the distances, all the angles, all the areas, proportionally, of course. Gauss proved that it is impossible to create an isometric planar map of the Earth's surface due to its varied curvature, hills, and valleys. And this theorem he called Theorema Egregium in Latin, that is the most outstanding theorem of his works. Even if there is no perfect map, we still need a map. We still want to get to the store. We use a so-called generally distorted map, just as this one in the slideshow, where nothing is perfect, but we certainly expect a structure-preserving correspondence, that is a morphism between the source domain and the target domain. If we see a three-way junction on the map, from which we have to choose the middle one and then turn left to get to the store, we expect the same structure and operation to be present and to be successful in reality. And this is the essence of morphism.
So, after this very concrete example of using a map, now we can ask is how does this idea of morphic relationship apply to thinking? And again, this will be like, okay, now this is very, very general, and we can think about thought structures. And this can be a thought structure in our head for human thinking, or it can be an artificial intelligence. So, any intelligent agent might have something like a thought structure, which we can define as a network of ideas, thoughts, or memories, basically any mental object that can be connected by association, this logical inference, or any mental action. So you have these points and you move along these edges connecting the points. And now we can understand thinking as following a path in your thought structure. And thinking is movement in this abstract structure. So now we can give an answer. So what is understanding? And it's like understanding is matching your thought structure algebraically. So that's a morphic relationship. It has compatible operations with some other structure. Okay, here's this just a very simple drawing of a very simplified idea that you might understand the cycle of water on Earth and in the atmosphere. And it's like, you see, it's like, well, yeah, it's a circular movement, and you can have a very simple model. You can have a thought structure mimicking that circular structure. And so if you have an algebraic matching, that means that you understood the phenomenon. And now we understand that it's like, what is explanation? Explanation is creation, is or just simply demonstrating of such a matching, that there is a morphic relationship between the thought structure and the thing that we want to understand, or the process we want to understand. Again, it's like it's the understanding is sort of an algebraic matching between the thought structure and the phenomenon to be understood. So now, what do we do with this? So what are the next steps in this research? So first, well, basically that's where we started from. Then it's like often we are not that happy with traditional mathematical philosophy, and we wanted to just think about why that's the case. And this is how we sort of got to this point that it's like, wow, it's like everything is basically a morphism, everything is could be metaphorical, and now we can review traditional mathematical philosophy in terms of explicit morphisms. There's another one, it's a bit more concrete. We can do a case study in a sort of an isolated, simplified word, and that's the board game. So we can study in Go puzzles, and where we can look at is like what does it mean as we have an understanding, and what does it mean understanding of the solution of the puzzle, and what does it mean? How do we explain these solutions? And it's like again our sort of conjecture is that this can be very well described in terms of morphisms. So certainly, if you think about the board position for the game and the movements there, the actual moves, that can be mapped to simply numbers. It's like how many points you get at the end. So that's just a very simple example. Then, of course, we are also thinking about sort of new methods in education. Well, that's the idea. That's the main purpose of thinking about traditional mathematical philosophy in the first place, that we want to understand that better how people think about it, and because we want them to understand mathematics better. That's why we are looking for sort of new educational material as well. However, this is of course a danger zone, because it's there is so much trouble in mathematics education. It's like you certainly don't want to make things worse, so you have to think a lot about how to make it better. But that's an ultimate goal too. So now, if this all sounded like very vague and very general and very short, then we just have a preprint available where we describe these ideas with more references and longer arguments. So if you are interested in that, please have a look at this, and thank you very much for your attention.